Okay, folks, picking up right where we left off. We're going to get into some more quantitative stuff, some calculations. So, yep, you got to do some calculations here at the end. So, I'm going to have some examples of that, okay? So, what we're getting into and what we're going to do calculations on is vapor pressure, okay? So vapor pressure is defined as the pressure exerted by a gas at a given temperature in equilibrium with its liquid phase. Okay, so if you're not understanding that definition, imagine this picture right here. Okay, I've got a container filled with liquid. I'm not going to slosh it around any because I had to fill up my water cup. And now, if I put a lid on this container and I wait long enough, we know that there's molecules in that liquid that are evaporating. So this blue arrow is evaporating. But then also there's going to be molecules that are condensing. That red arrow. Okay? And they're going to be going back and forth and back and forth. Evaporating, condensing, evaporating, condensing. Which is what we would call equilibrium. Okay? Once this process has steadied out. And so now there's going to be a gas in what we call this headspace. Okay? So when we have a container with a liquid in it and it's closed off, the space above the liquid, we call that the headspace. And there's gas in that headspace. Specifically, there's vapor. Okay? Really, it's vapor, which is a gas that has come from a liquid. All right? And that vapor will add pressure. Okay? Or it has pressure, right? There's gases in there. They're colliding with the walls of the container. All right? And so the force that is exerted by that gas is the vapor pressure. Okay. So what about this other definition here? Normal boiling point. So the temperature of which the vapor pressure of the liquid equals 1 atmosphere. So that is actually our definition of boiling. Okay. So we imagine let's say we've got a pot of water here. Okay. There's my little handle. Okay. And so I've got this pot of water and like there's all these, bubbles, and then we've got steam rising off the liquid. So it's boiling, okay? So what this means is, let me change colors. When a liquid is boiling, the force that the liquid is exerting on the atmosphere, oops, I did the wrong color. So the force that the liquid is exerting on the atmosphere is the same as the force that the atmosphere is exerting on the liquid. So this is the force of the atmosphere pushing on that liquid. We know that as atmospheric pressure. So let's suppose that that's 1 atmosphere. Okay, we're boiling a pot of water at 1 atmosphere of pressure. All right, so that atmosphere is pushing 1 atm on the liquid surface. When that liquid pushes back, so in other words, when the vapor pressure P vape equals 1 atm, by definition, the liquid is boiling. That's what boiling means, when the vapor pressure of the liquid is equal to atmospheric pressure. Okay? So what factors determine vapor pressure? I, M, F, you guessed it, intermolecular forces. The strength at which molecules are stuck together, right? The stronger an intermolecular force is, the lower the vapor pressure will be. So let's write that down. So strong I, MF. Oh, that's terrible. Okay, here we go. Let's try again. Strong IMF equals low p-vape. Weak intermolecular forces equals high vapor pressure. So if you think about this, if something has very strong intermolecular forces, it's going to be stuck together in the liquid phase. There's not a whole lot of it that's going to evaporate. Okay? So it'll have a very low vapor pressure. Consequently, to get that strong intermolecular force liquid to boil, right, to get it to where its vapor pressure is a full 1 atmosphere, you have to really heat it up. So this means it's going to have, I'll say, large, oh my gosh, I'm getting sloppy, you guys. Large T boil, okay? So something that has a high vapor pressure or weak intermolecular forces will have a small boiling point. So in other words, when it's got strong intermolecular forces, it's going to have a low vapor pressure. Consequently, it's going to take a very large temperature to get it to boil. When something has weak intermolecular forces, it has a very high vapor pressure, so it evaporates really easily. Consequently, it doesn't take a lot of energy or temperature to get it to boil. Okay? So here is a graph of several different liquids and their vapor pressures. And so this line right here, this dotted line at 760 torr, so we remember that's P atmosphere, this dotted line, okay? And so that's the atmospheric pressure, you know, at sea level, right? So we know if you go up to Colorado or outer space, the pressure will be much less. And so we'll talk about that in a moment. But now if you look at water here, let's pick on water, the blue curve, okay? So if we follow through this now, at, let's say, room temperature, somewhere around here, the vapor pressure of water is quite low, okay? And you notice as we heat the water up, it increases exponentially. So exponentially. So there's an exponential increase in vapor pressure with temperature. Okay? And you notice once you start really heating up that water, its vapor pressure really takes off. And when its vapor pressure is equal to that of atmospheric pressure, it's boiling. And if you notice here with water, look at this. If I follow all the way down, yep, there it is, 100 degrees Celsius. Okay? If we look at that octane example like I've been talking about, right? Octane boils at a much higher temperature than water. And then ethylene glycol boils at a crazy high temperature. So ethylene glycol has very strong intermolecular forces. All right? So there's an exponential increase of vapor pressure with temperature. And when that vapor pressure equals the pressure of the atmosphere, it boils. So now what happens if you're in, let's say, Colorado in the mountains somewhere, and maybe the pressure is like, I don't know, 650 torr, okay? So suppose you're right, like way high up, okay, in the mountains, okay? So if you follow this line now, you notice here, water would actually boil at less than 100 degrees because it's going to boil at whatever temperature makes its vapor pressure equal to the pressure of the atmosphere, right? So when you're way high up in altitude, all liquids will boil at a lower temperature. And in fact, if let's say you were at the pressure of outer space, like, you know, somewhere like near zero, right? As soon as, if you had a container of water, so let's imagine this. So let's say you have a container of water and you're doing a spacewalk. Lucky you, okay? As soon as you open that container, the water would boil instantly. assuming that it didn't freeze instantly, right, from being super cold in space. So if we play this caveat, like let's suppose, the water is not frozen, right? It's got some amount of temperature, okay, to keep it as a liquid. It would boil instantly. And we can do this experiment in the lab all the time where we boil water or we can boil another liquid at room temperature, which is really cool, right? It's kind of contrary to your everyday experience boiling a liquid at room temperature, but all you have to do is pump vacuum, right? Pump a vacuum over that liquid and you can make it boil without adding any heat at all, which is really cool.